Let's continue with high-speed steels. And once they were introduced into the industry, they actually let people do the machining operations at higher speeds than the carbon tool steels. And that's why actually people name this type of cutting tool material as high-speed steels. And where we can use high-speed steels, especially for the cases where you need to have high positive rake angles. This is a low rake angle, this is high rake angle. If you want to apply such a rake angle, then it's better you use high-speed steels. Another thing, you can use them for interrupted cutting operations since their toughness properties are good, their impact strength is good compared to the other cutting tools, especially for such interrupted cutting operations. It's better you use HSS. Another thing, if your machine tool has less stiffness, then it's better you use high-speed steel since its toughness is good enough. And again, related with the case B, due to the interrupted forces, you have no problem. It's quite have good resistance to such cases. Another application area is the complication of the tools. If you have designed special forms for your cutting tool materials, then it's easier to manufacture high-speed steels than the other ones. Actually, we will discuss them in a moment. They are quite complicated and they require more complicated manufacturing operations. But the manufacturing of high-speed steels is quite easy. So for complicated tools, it's better we use high-speed steels. And we know that their toughness and impact strength is good, but they have lower hot hardness compared to other cutting tool materials. And due to this, you can only machine at lower speeds compared to the coated carbides, other carbide tools, ceramic tools, cubic boron nitride, such kind of cutting tool materials. We prefer them for lower cutting speeds compared to these, but higher cutting speeds compared to carbon tool steels. We basically have two types of HSS. The first one is molybdenum series, and as the name implies, we have more molybdenum, as you see, 10% inside this one, and along with molybdenum, there are also chromium, vanadium, tungsten, and cobalt as alloying elements in the matrix. But comparing with tungsten series, we have obviously more tungsten, up to about 20%. Then again, we have other alloying elements like chromium, vanadium, cobalt, and with the help of them, we try to increase some specific properties. And in all of these, we have some carbides, and the volume of carbides is usually around 10 to 20%. And by the way, what is a carbide? Carbide is a chemical compound composed of carbon and metals. And how do we manufacture high-speed steels? As I mentioned, it's very simple. We can simply cast them or roll them, forge them, and this is one of the simplest manufacturing operations. And furthermore, if you want to improve the properties, if you want to improve some other mechanical properties of your cutting tool, then you can simply apply some coating, chemical vapor deposition with chemical vapor deposition or physical vapor deposition to improve their overall performance. And as you have seen in these two types of HSS, we have different alloying elements. Why do we add them? They actually improve some specific mechanical properties. For instance, chromium improves toughness, very resistance, high temperature strength. Tungsten and cobalt have similar effects. For instance, they improve the strength and hot hardness. So if you have a tungsten type of HSS, then probably its hot hardness value is a bit higher. The thing is here that adding such, so we have a matrix, we are trying to add different alloying elements to have better mechanical properties. You don't need to memorize them. I don't even, for instance, remember what is the effect of molybdenum, but I know that once you add such items, you will be improving some specific mechanical properties. Then what do we have? We have cast cobalt alloys, as the name implies. In this one, we need to have more amount of cobalt. And you see about up to half of the matrix, sometimes composed of cobalt. Then we have chromium, vanadium, or tungsten type of alloying elements. The problem is that they don't actually have high impact strength or high resistance to impact forces, and that's why they're not preferred for interface cutting operations. They are mostly utilized for deep and continuous roughing roughing operations, and you can do it at quite high speeds, so that your tool moves actually at high speeds compared to the previous cutting tool materials. Then we have a bit better type of cutting tool material. These are called as carbides, and the previous ones actually were not suitable for let's say difficult materials, since the previous ones lose their hardness values at high temperatures. But now with carbides, they were introduced around 1930s. We can now machine difficult materials even at high speeds and high temperatures, since their strength and hardness values do not change much at these, let's say, temperature levels. And we have two types of carbides. Tungsten carbide is one of them, and the other one is titanium carbide. The difference is that the type of carbide actually in the matrix we have is a bit different. Obviously in the tungsten carbide we have tungsten carbide particles. Let me draw a kind of assume that this is a side view of an carbide, and we have such little carbides. And if it's made of tungsten, then it's called as tungsten carbide. And this is how we can represent a kind of a tungsten carbide cutting tool. And we manufacture them by using powder metallurgy. We haven't discussed the type of this manufacturing process, but in that, what we have powders of carbides, powders of cobalt matrix. So what we do, we put them inside each other, mix them, and then apply some pressure and obtain this specific cutting tool. And these are, I think, the things I mentioned. The size of these carbides are not too much, up to their sizes are up to 5 micrometers. And we usually have them in the form of inserts. And the inserts are usually manufactured with the help of powder metallurgy methods. These are some examples. I also have one on my desk. It's a diamond type. And as you see, it has 4 edges, 4 cutting edges. And also it has 4 more at the back side. So we can say that if one of the edges of this cutting tool becomes dull, then you can simply rotate it or turn it upside down and try to use it. For instance, this one has 4 cutting edges. And another thing about these inserts is that, as you see, they have specific features, specific geometric features on their surfaces, and they are some kind of chip breakers. With the help of them, we can mostly produce discontinuous chips. And as you know, having discontinuous chips is desired. They have better properties in order to remove heat, in order not to scratch the surfaces. We always try to have discontinuous chips, and it's possible with these embedded chip breakers on the inserts. And this is a second type of carbide tools, titanium carbide. The idea is again the same. The only difference is that the type of carbide in the cobalt matrix is different. This is titanium carbide. And another difference is that due to the titanium, we have higher wear resistance compared to the previous type of carbide. But the problem is that its toughness is decreased, since we know that there are quite an inverse relationship between the wear resistance or hardness and the toughness. Once you increase one of them, then the other one decreases. This is another example showing how we can use inserts, since these are little cutting edges. So we need to have a kind of a tool or a tool holder so that we can easily put them inside here, clamp it, and use it in our machine. It's another nice thing showing the effect of edges. Once you have no edges, then the strength of this insert is higher. Another thing is that once you don't have any edges, then we have less chipping, less breaking. So it's better you make use of such kind of things, such kind of shapes for the inserts. Otherwise, if you, let's say, move to this one, then probably you're going to have some chipping and breaking of these edges, corners, and then also your strength will be decreased. So what are the functions of inserts? First of all, they control the chip flow. They may have some angles, so they will rotate or actually move, decide on the direction of the chip actually. On the other hand, they eliminate long chips, continuous chips. They try to make them discontinuous. Heat decrease the heat generated, since the generated heat is carried away with the help of these discontinuous chips. Another thing is that they have less tendency for vibration and chatter, which decreases the quality of machining. So as you see, chip breakers have lots of advantages. And that's why people these days prefer to use chip breakers instead of longer single. Let's continue with the coated tools. After 1960s, people started to develop actually new workpiece materials having very good strength, toughness properties, and they were quite difficult to machine with the available cutting tools. Like carbides, it wasn't possible to machine these materials at high speeds or efficiently. So what they did is that they started to use coatings. They started to apply coatings on the available carbide tools. And the advantage of these coatings are that, first of all, they decrease the coefficient of friction on the rake face, on the flank face, so that less heat will be embedded in the cutting tool and the temperature of the cutting tool will be kept at lower temperatures. Then with the help of different type of coatings, they increase the wear resistance and cracking so that the life of the cutting tools are improved. And another advantage of coatings is that with the help of them, the hot hardness values, the resistance of these cutting tool materials to impact forces is improved. And lastly, with the help of these coatings, actually, we have a kind of a barrier between the tool and the generated shapes. And once you apply such coatings on the carbides, then you can use the same carbide tool at much higher speeds. For instance, here it says that the life of the tool is improved 10 times compared to the uncoated tools. And we can have a look at this figure here. We have timeline on the x-axis and we have machining time on the y-axis. If you look at the carbon tool steel, if you assume that you have a specific part, let's say in 1900s, we were spending 100 minutes to machine the same workpiece. But once the technology behind cutting tool materials improved, we now use less time, spend less time on the machining of the same part. If you look at here, especially these time periods, now we have much powerful coatings. Even we can apply 3 or more coatings on the same cutting tool. So that's why in even less than a minute, we can machine the same product. And in the 1900s, as you see, we were spending 100 minutes, but now we can do the same machining in less than a minute. Now let's have a look at the type of typical coating materials. We make use of titanium nitride, titanium carbide, titanium carbonitride, and aluminum oxide. It's some kind of a ceramic coating, and their thicknesses are not too much, up to 15 micrometers. And we usually apply them by using two main techniques. What are they? The first one is chemical vapor deposition and physical vapor deposition. We're not going to discuss the details, but please make sure that you read the details of these processes or watch kind of some videos, informative videos, so that you understand what is going on in these deposition processes. Let's have a look at some main properties of these coating types. The first one, titanium nitride, is mostly applied to decrease the coefficient of friction. But along with a decrease in the friction coefficient, we also increase the hardness a little bit increase the resistance of this tool to high temperatures. And with the help of these, the life of the cutting tool is improved. Let's have a look at this figure here. We have two cases, two tools here actually. This is titanium nitride coated tool. This one, let me draw it. This is the coated version, and the other one is uncoated version. And we can clearly see that in the coated version, we have less flank wear. But in the uncoated one, we have much more flank wear. And if you remember, this flank wear is highly related to the cutting tool life. So once you have too much wear, then we can easily say that the life of that cutting tool is less compared to the cutting tool which has less flank wear. So in summary, titanium nitride increases the life of the cutting tools. But we have a problem about this titanium nitride. We cannot use this cutting tool material or coating approach at very low cutting speed. Since they're not actually chemically inert, we may have some chips actually embedded onto the flank face. So in order to remove this issue, you may use some cutting fluids or apply another type of coating. Then we have titanium carbide coating. This is mostly applied to increase the flank wear resistance so that we will have less amount of flank wear on the flank face. Then we have ceramic coatings. These are mostly used to increase the chemical inertness of the cutting tool materials. With the help of them, we can do the machining at even low cutting speeds. And the most commonly used type of ceramic coating is aluminum oxide. And we can have these coatings on top of each other. This is actually the main approach in coated tools or coated carbides. People apply many of these on top of each other so that we will have very nice mechanical properties, not just chemical inertness, but having low friction coefficient, having high hot hardness values, increasing the life, increasing the flank wear resistance. So we want to have all these mechanical properties, and it's only possible with multi-phase coating approaches. We have an example here, for instance. You see we have multiple phases of coatings, multiple layers. At the base, we have a thick carbide substrate so that we will give a shape to our insert, and its resistance to the plastic deformation will be quite high, especially at high temperatures. Then we may have a bit thinner carbide substrate so that it will increase the toughness properties. Then we have some titanium carbon nitride, aluminum oxide or ceramic coating, and lastly titanium nitride so that we will have less friction. As you see, with the help of these, we have many nice properties, mechanical properties employed into the cutting tool material. Then we have last type of coatings. It is diamond coatings. And in order to do these coatings, we make use of polycrystalline diamond. Actually, these are very little diamond particles. We apply them onto the carbide tools or different type of tools, again, to improve their hot hardness properties. But the problem is that we can only use this diamond coated tools with non-ferrous metal. You cannot use these for ferrous metals. What happens once you use them with ferrous metals, since they're not chemically inert, we will have some reaction and probably some particles from the tool will be removed, and you will no longer be able to do the machining operation. But that's why actually mostly use this diamond coated tools on non-ferrous metals, on abrasive materials which have higher hardness values, or on some special type of fiber reinforced and mathematics composite materials. And lastly, on graphite, we can make use of this polycrystalline coated, diamond coated actually tools. Their main advantage is that the hot hardness value is very high. You can remove material from hard work pieces. And we can do this deposition, apply this polycrystalline diamond onto the uncoated tools by using, again, physical or chemical vapor deposition methods.